Alright, so like I say, really nice work on the exam. Didn't really see anything that concerned me, as a matter of habit. So, truth table for the following expression. A number of people put in a 0 for A, B, C all equal to 1, including myself when I was first putting together an answer key. I don't know why, but yeah, if A, B, and C are all 1, then certainly all 3 of these terms are true, so the OR is also true. So, so there's 4 expressions that are true, and it's basically min terms 3, 5, 6, and 7. So if you do this in pieces, A and B is 0 until these last 2 entries. B and C is 0 until the 4th and the 8th entry. And AC is 0 except for those 2 entries. And then what do we call this? F. F is now just the OR of this column, and this column. So first row is 0, second row is 0, third row is 0, fourth row is 1. And then this is 0, 1, 1, 1. So there's a truth table. And if you want to write this in compact form, min terms go like this. Okay, and those are also the ordering for the max terms. So we can write f of a comma b comma c. It's a sum of products, so we sum up the min terms where f is equal to 1. So it's min terms 3, 5, 6, and 7. If you want to write it as a product of sums in compact max term form, that's a product, and you write the max terms where f is equal to 0. So that's going to be terms 0, 1, 2, and 4. And the nice thing, if you write it in max term or min term form, is you'll have whatever numbers you don't have here, you'll have there, and vice versa. Right, because these are the zeros, these are the ones. So you should end up with a total of 8 terms, and they shouldn't overlap. All right, the binary calculations. One issue a few people did was they only used 6 bits to write their numbers instead of 8 bits. You got to use 8 bits, right? In most cases, if you only used 6 bits, you got a wrong answer somewhere along the way. So 47 divided by 2 is 23, remainder 1. 23 divided by 2 is 11, remainder 1. 11 divided by 2 is 5, remainder 1. We got lots of 1s. 2 divided by 2 is 1 with a remainder of 0. 1 divided by 2 is 0 with a remainder of 1. And then 0 divided by 2 will be 0, remainder 0 forever. And remember, it's this number which moves down to the next line. And then it's these remainders that give you your final answer. And so it's 0, 1, 0, 1, 1, 1, 1. And if you need 8 bits, you got to add an extra 0 into the front. So there's an 8-bit representation of 47. And if you do the same thing for 67, that'll turn out to be that. So it's 64 plus 3. And then it asks you to write minus 67 in binary, so you need to take the 2's complement. So minus 67. So complement and then add 1. Or use your trick where you move from the right, keep the first 1, and then complement everything. So if we complement and add 1, let's do 1, 0, 1, 1, 1, 1, 0, 0, plus 1, 1, 0, 1, 1, 1, 1, 0, 1. So that's minus 67. This is 47. And then it says add your answers from A and C to write 47 minus 67 in binary. So now you're doing pencil and paper addition. So 1, 0, 0, 1. Oh, that's a parenthesis. I don't know why I have that. So 0, 0, 1, 0, 1, 1, 1, 1 plus minus 67, 1, 0, 1, 1, 1, 1, 0, 1. So add them together. 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. 1, 1, 1 is 1, carry the 1. 1, 1, 1 is 1, carry another 1. 1 and 1 is 0, carry the 1. 1, 1, 1 is 1, carry the 1. 1, 0, 0 is 1 with no carry. And 0, 0, 1 is 1. This is your answer for 47 minus 67. And you would want to show this, you always want to show your work, right? You'd want to show your work and you'd want to make sure that this number is clearly marked as the answer to the question, what is 47 minus 67? Okay, and then it asks you, convert that number that you got in part D into decimal. So how do we convert a 2's complement number into decimal? Well, you have to look at the first digit and see if it's a 1 or a 0. If it's a 0, this is a positive number, you can just add up the powers of 2. If it's a 1, this is a negative number. So the best way to convert this to a positive is take the 2's complement. So the negative of 47 minus 67 is 0, 0, 0, 1, 0, 0, 1, 1 plus 1. So that's 0, 0, 1, 0, 1, 0, 0, 0. And add up the powers of 2. This is equal to 20. So the negative of your answer is equal to 20, which means your original number is equal to negative 20. And then you can observe that that's also what 47 minus 67 is, right? So your answer checks out. Converting this to, to find out what value it is, you can subtract 128 from it, and it mostly works, but it doesn't always work. In particular, this is actually the number negative 128. And you know it's negative because there's a 1 in the most significant bit, but if you subtract 128 from this number, you get 0. So it's a special case you got to remember. But take the 2's complement, and you'll find 128, and so this is negative 128. If you do this and you get the wrong answer for, say, negative 67, right, you make a mistake in converting it, and then I ask you to calculate 47 minus 67, and you somehow magically come up with the binary version of negative 20, you don't get credit for it, because you made a mistake in the addition, okay? So even though you should get negative 20, right, you're trying to add your answers from A and C, add whatever answers you got, and if you end up with negative 16 or 5,000,007, right, if you did the addition correctly, you'll get credit for it. And you know, if you double check and you figure out negative 20 looks like this, you can put a note there and say, I know I should have gotten this, but I did something wrong. But don't just put down what you think the answer should be, unless it comes from the work you're showing. And then same thing, E, if you came up with something that wasn't negative 20, convert it, find out what that number is, right, and write that down. All right, question 3. Anything else on question 2? I think that was it. So question 3, make a Kmap, simplify, find a minimal SOP, find a minimal POS. So here's what the Kmap looks like if you write in the ones and the don't cares. Remember, for don't cares, you put them into your Kmap, but you're not required to cover them. Okay, so you're required to cover the ones, and there's 4 ones, and then you got 2 don't cares. Well, if you include those don't cares, you can find this nice big 4x1 rectangle to cover those ones, and then have a 1x2 to cover the corners. If you don't put in the don't cares, then you get a 1x2 and you get a 1x1 down here. So your minimal expression is A bar, B bar, D, or C bar, D. And if you covered with extra rectangles, you lost a few points. If you didn't use the dashes, you missed a few points. Once you've got this coverage, you don't need to put a rectangle here because you've already covered that one and that one. And if I put a rectangle here, I still need to cover this one, so I'm still going to have a rectangle, and I'm going to cover that upper left corner. So an extra rectangle there, totally extra term. Your expression is still a correct expression, it's just not as minimal as it could be. Alright, so product of sums, you fill in the zeros and the dashes, and you have to cover all the zeros, and you can optionally cover the dashes. And you get a few things. You get a big 4x1 rectangle right here. That's pretty required, because you got to cover that one up there. May as well do a 4x1. But then you got these zeros on the side, and you got at least 3 different ways to cover these. One is to cover these 4 with a long skinny rectangle, and then do a bent 2x2 to cover these lower spots. Another is to use a 2x2 to cover those upper ones, and then a 2x2 to cover the lower ones, and you're double covering the middle, but that's okay. And there's a third option somewhere. Oh, you can put a big long skinny rectangle to cover the bottom 4, and then do a broken 2x2 to cover the top 2 on each side. And any of those will get you a minimal expression, but they're different expressions. But they're all, you know, a product of 3 terms, where each of the terms is a sum of 2 terms. So they're equally reduced. Whatever you come up with, these should definitely be a product of max terms. So the individual things should be ORs, and you should be taking a product, an AND of all of those. That's the product of sums form. Sum of products, you should be taking a bunch of ANDs, that's the product, and then summing them together, a bunch of ORs. That's sum of products. Make sure you only use 1x1, 1x2, 1x4, or 2x2 rectangles. No 1x3s. And I think everybody wrote correct expressions, which is amazing, because that never happens. So particularly on the product of sums, right, if we want this rectangle that goes like this, C is 1, D is 1, that's C bar or D bar. And I think everybody got those right, which is awesome. That's going to help a lot. So no major concerns on the Kmaps from what I saw. All right, circuit design. Circuit design was pretty good too. So design a circuit with 3 switches, LEDs, resistors, gates. So when A is open and B and C are closed, the LED is on. When A is closed and B and C are open, the LED is on. The bonus point of this question is that if you have the wrong idea of what open and closed do, you still get the right answer because it's symmetric. So let's write a truth table. So well, first of all, it asks for a system diagram. So system diagram, 3 inputs, A, B, C, and output, I'm just going to call the output LED. The output goes on the left of the equals sign, so you can kind of call it whatever you want because you're not writing equations involving the output. But the inputs, usually you want a single letter or a letter and a subscript or something like that because you're putting them next to each other and ANDing and ORing. So there's a system diagram, truth table. So closed means 0, right? If we wire up our switches in the usual way, when a switch is closed, that place that it's connected to is shorted to ground, so that's a 0. So A is open and B and C are closed, so A should be a 1, B and C should be a 0. In that case, the LED is on. A is closed, B and C are open. That's this case down here. And every other case, the LED is off. So LED is A, B bar, C bar, or A bar, B, C. That doesn't look right. That's not right. No. That's right. Alright, so there's your equation, and then sketch of schematics. So, schematics looked good. Switches are still tricky. Okay, so you've got 3 inputs, A, B, and C. So you want 3 switches labeled A, B, and C. And make sure you label the switches themselves, not some point down the circuit that's connected to the switch. Okay, because you want it to be as unambiguous as possible. So these get pulled up through a 1K to VCC. And the other side of the switches get grounded. So LED should be A, B bar, C bar, or A bar, B, C. So I'm going to want inverters on each of these. Inverters have to have that little circle on the outside. Okay, this is actually also a valid logic symbol, but it's not an inverter. It's called a buffer. If you put in a 1, you get out a 1. If you put in a 0, you get out a 0. It's kind of like a wire, but it actually bumps up the current so that if you're trying to drive something like a large light or a motor, you get more current coming out from whatever's producing this. So that's definitely not an inverter. Okay, that just passes the input to the output. So if you want to invert, make sure you put a circle on the output. And then we want A ANDed with B bar, ANDed with C. And if you have 2 input gates, you can use these 2, take the output ANDed with another one. But I didn't ask you for part numbers and stuff. And then we also want A bar ANDed with B. I'll make this really tricky to read. ANDed with C. And sometimes I'll label these just to help me keep straight what I'm doing. This output here is A, B bar, C bar. This output is A bar, B, C. And I want to OR those together. So I'll put those into a 2 input OR gate. and that output will be my signal, which I'm calling LED. And we want to drive an actual LED, an actual light, so this should go into an LED, and that goes through a resistor and goes to ground. So there's a full logic diagram. And if I were doing this for a lab, I'd want to put on pin numbers, I'd want to put on parts numbers for these, have a component ID block, right? But I said you don't have to do that. And nobody did it, which was great. So, so switches are tricky, right? There's some people who connected all three of these together and then put one resistor going to 5 volts. If you connect these together, A, B, and C are forced to take on the same value. They're shorted together. So you need separate resistors on each one. LED should go in this direction, should have a 1K resistor either here or there, but somewhere in series with the LED, and then connect it to ground. If you connect this to power and put the LED in the other direction, this is going to do the opposite. The LED is going to be off whenever the output's 1. It's going to be on whenever this output's a 0. So you're basically getting the complement of this truth table in that case. Make sure your switches are labeled. Make sure your output is labeled. What else? And don't draw this the way we draw fuse maps, right? This is technically not a valid circuit. Right, this has got the output of 2 gates wired together to each other, and this has got 3 switches all shorted together on the same line going into an AND gate, right, a 1-input AND gate. That's a shorthand we use when we draw fuse maps because we're not building that part of the circuit. The fuse map part of the circuit is fixed. It's always exactly the same. All we're doing is showing where we want to connect things together by drawing little X's at the crossover points. So we use an abbreviated view of the circuit, which is using these tricks. Draw all of these on one line and draw all of these on one line. But it's not a valid circuit diagram, right? And if you tried to build this, you'd short out your components. So we don't ever draw that when we actually do wiring diagrams. It's just an abbreviation. All right, I think that was all I saw that I wanted to mention. So questions about that one? All right, and then true, false, these were really good too. So any gate can be implemented with a collection of NOR gates, that is true. Any gate can be implemented with a collection of AND gates, that is false. You can't make an inverter. Among other things. What type of component is used to route from multiple inputs to a single output? That's a multiplexer, or a MUX. Sum of products will always require fewer gates than product of sums. That's not true. It might feel like it though. You can implement any Boolean function of 4 variables using a 16:1 MUX. That is also true, right? We did some examples of that. Name one reason why we should minimize an equation before implementing it as a circuit. Basically, if you minimize, it's less hardware. It's less wires, it's simpler, it's less power, anything equivalent to that. And then LED should be placed in series with a resistor in order to improve the speed of your circuit. That's false. You put LEDs in series in order to reduce the current going to the LED. Has nothing to do with speed. In fact, it actually slows down the circuit. In some cases. So, and the multiple choices were good too. All right, so any questions on the exam? Yeah.
Back to the first one. So when you want us to write stuff in max term form, do you want us to like put just the zeros in the parentheses?
You asking about how to write it, or?
Yeah, just how to write it. Max term form.
So, compact max term form You could do something like this. So max term means it's a product. So you could say M0, M1, M2, M4. Or you could do just product of 0, 1, 2, 4. So this is called implicit and this is called explicit form, but they're both compact. Basically, if we're doing a product, we know we've got max terms, so the M's are kind of redundant.
One more thing I want to clarify. So on number 3, you'll also want us to include the don't cares and the Kmap.
The don't cares will help you get a smaller circuit usually. So you always want to consider them. Now if covering them doesn't help you, then don't cover them.
Right.
So if you have a Kmap like this, right, I would cover these two ones with a 1x2 rectangle and I'd be done. There's no reason that I would cover those dashes because that's just going to add more hardware. It's going to be another term in my expression. And if I cover these, I'm saying these should be 1, but I don't care if they're 1s, right? But if I had a 1 sitting out here, I would go ahead and cover these two. And that's going to be better than just covering this 1 by itself.
Okay.
So they're optional covers. So other questions? All right, questions about the homework. So I graded question 2, which was looking at that crazy circuit with some ANDs and XORs and a big 3-input AND and trying to simplify it. So this circuit down here. So this is A0, A1, this is A2, A3, this is A1 XOR A3. Those three things I just said get ORed together to give you this, and that gets ANDed with the first and third things that I said. And you get this big long expression, right? So to find the minimize logic function implemented by this, you got to go to a truth table. So here's all the values for A0 through A3, and start writing columns for the pieces of your expression. So I'm writing a column for the output of this AND gate, the output of that AND gate, and the output of this XOR. So there's A0, A1, A2, A3, and A1 XORed A3, and just fill in your 1s and 0s. And then those three columns get ORed together to give you this output here. So I ORed these first three columns to get this fourth column. That's the OR of the first three. And then you take that first column, the third column, and the fourth column, you AND those together. So now I just look at these three columns and AND them together, and I find a 1 in exactly 2 spots. Term 3 and 7. And if you make yourself a Kmap, you can simplify it one step, and so F will turn out to be A0, A1, A3 bar. So all that circuitry turns into a single 3-input AND gate with one inverter. All right, so any other questions? So I feel like everyone's in really good shape as far as combinational circuits go, okay, which is awesome because everything we're doing from here on out are these sequential circuits, these circuits that change over time and that depend on past values, past states of the system. And we're not going to, do random Kmap problems for homeworks and so on. going forward, but you're going to want to use Kmaps, for example, to build some of these sequential machines, because these sequential machines contain combinational pieces, and you want to be able to build those with fewer parts rather than more. So we're going to be using what we've done so far in everything that comes next. But the focus of our work is shifting to strictly these sequential circuits and these sequential behaviors. So let's talk for 15-20 minutes on more of these memory devices, these latches that we started to talk about, which will lead us to flip-flops, and then we'll take a break, and then we'll talk about how we use these things. And the goal this week is to learn how to analyze circuits that have this sequential behavior. So we're going to learn how basic building blocks, latches and flip-flops, and then we're going to look at some complex circuits and analyze them. We'll probably get to that on Thursday. And I'll post homework Thursday, which we'll be doing a week, and that'll be a bunch of questions analyzing circuits. And then next week we're going to work on synthesis. It's the other direction. We're going to say we want a circuit that has this behavior. How do we build it? How do we design it? Okay, so this week is analysis. Here's a circuit, tell me what it does. Next week is synthesis. Here's what I want the circuit to do. Show me the circuit that'll do it. And that'll pretty much round out the whole aspect of combinational circuits. And then we're up to week 8. And we only got 3 weeks left. So then we're going to start talking about something called Verilog. And Verilog is a nicer way to design and work with some of these circuits using something like a programming language. And we'll probably spend the last 3 weeks mainly playing with Verilog. And Verilog, if it decides it likes you, is really nice. It took 3 years for it to like me, so. But I think I know how to make it more amicable. All right, so let's review. We started with an SR latch, which was this device with 2 inputs called set and reset, and an output called Q. I'm going to ignore Q bar again. So 2 inputs, 1 output. And the behavior was, if S and R are both 0, nothing changes. It's just stable. If you raise S to a 1, the output gets set. It turns into a 1. If you raise R to a 1, the output gets reset. It goes back to a 0. And the idea is S and R are normally both low. And you can bump one of them up, and the latch sets. You can bump up the other one, and it resets. And if it's already reset and I bump this, it doesn't do anything. And if I bump set again, then it sets. And we don't usually think of turning on both set and reset at the same time. Okay, like I said, that's like flooring the gas and pushing down on the brake as hard as you can. Something will happen, but it depends on how the circuit is built, whether it'll pay attention to the set or pay attention to the reset. But it's not the intended mode of behavior. So that's an SR latch, and we used this to design a circuit that was a little more perhaps useful, called a D latch. So a D latch still has 2 inputs, but one of them is D, that's a data input, and the other one is the latch or the gate, the thing that says, I want you to pay attention to D. And so if the latch is high, if the gate is open, whatever goes in D comes out on Q. When the latch changes to a 0, whatever value is in here gets stored in there. And it ignores D, and it just shows the value that's stored inside. So you can raise a latch to 1, data values come in and appear on Q. Drop the latch to 0, and whatever value D had at that moment, that's the value saved in this device. And you can see it on Q. And that's a pretty useful circuit. And one thing we can do with D latches is we could build registers. So if each of these is a D latch, and here I'm showing D on the top and Q on the bottom, and let's assume I'll just use L for latch. Let's assume our latch input is over here on the right. Well, if I take all of these latches and I tie them together, I can take a 4-bit number, D0, D1, D2, D3. I can call this green line latch, which is feeding into all of my latch inputs, and I can call these outputs Q0, Q1, Q2, Q3. And now, if I raise this latch to a 1, whatever 4 bits are up here on the D inputs will get loaded into these 4 latches. And when I set my latch to 0, those 4 values are saved in these 4 latches, and they appear on these 4 outputs. So this is a 4-bit memory. Yeah?
So they don't actually appear until after it's...
No, they actually go through as soon as you raise the latch.
Oh, really?
So if latch is 1, D just goes straight through to Q.
Right.
That's an important distinction, by the way. So that's worth a timing diagram. So here's D, here's latch, and here's Q. Let's suppose Q starts off low. So D's doing all kinds of crazy stuff. It gets totally ignored. If latch is low, Q is stable. At some point the latch goes to a 1. If D rises up, Q will rise up. If D drops again, Q will drop again. But at the point where the latch drops, that value of D is now latched into the device. And if D changes over here, again, it completely ignores that. And then when the latch goes to a 1, Q will pay attention to the value of D, and it'll show you whatever that value is. So that's nominally useful. We can store, numbers or characters, or the Library of Congress if we have enough of these things, and put data in here. When we want to save it, just raise the latch to 1, drop it back to 0, and all those bits are stored in here. But this is really interesting. The fact that while the latch is high, whatever happens to D is going through and affecting Q. Okay, why is this a concern? We want to build computers. So, how many people here have done programming in any language? All right, so if you say something like x equals x plus 1, what does that say? What does that do?
You're incrementing x by 1.
You're incrementing x by 1. It says take the current value of x, add 1, set x equal to that. Mathematically, this is gibberish, right? If x is an integer or a real number, x is never equal to x plus 1. Can't be, right? But that's not what this is. This is an assignment statement. So in some languages, you write it like this. You say take x, add 1, and store that back into x. Okay, so it's a read, modify, write. Let's see if we wanted to build hardware that could perform this function, that could take x, add 1 to it, and store it back into x. Well, we've got all the pieces. So let's suppose x is a 4-bit number, so 0 to 15, or maybe -8 to 7 if it's 2's complement. But it's a 4-bit number, and so let's store it in a register. So we're going to have Q0, Q1, Q2, Q3, and 4 inputs, D0, D1, D2, D3. And we're thinking of this as the number x. And it's got its load inputs. Which get tied together. So that's the load or the latch input. Alright, so there's X. How do we add 1 to X? Use a 4-bit adder. You know how to make adders, right? You've done half adder, full adder for lab 2, so do a half adder and 3 full adders. You've got a 4-bit adder. So let's make a circuit over here, which we'll call 4-bit adder. And so it has 4 inputs. Let's call them A0, A1, A2, A3. And it's also got inputs B0, B1, B2, and B3. Well, if I want to add 1 to a number, right, my first number is going into the A inputs. My second number should be 0, 0, 0, 1. So I'll take B1, B2, B3, connect those to ground. I'll take B0, connect that to 5 volts through a 1 kilo ohm resistor. Now B is hardwired to be the number 1. 1, 0, 0, 0. And it's being added to A. And here's your output bits. Sigma 0, sigma 1, sigma 2, sigma 3. So this is our number X. This is our number X plus 1. Agreed? So if we want to load that back into X, all we got to do is feed these back into the D inputs and then raise the load line. And X will get incremented. So let's make some connections here. This goes up here. This goes over here. This goes here, and this goes there. So somehow we have this circuit inside our computer, maybe because we have an increment instruction. And to increment X, all we got to do is take the load line, raise it to 1, drop it back to 0. And now X plus 1 gets loaded into X. We've done our instruction. Making sense? All right, so there's a problem. Let's suppose X starts off at 0. So each of these is a 0. So we get 0 and we add 1 to it, so the output of the sum here is 0, 0, 0, 1. And those are carried around to the D inputs. Alright, so X is still 0. If we raise the load line to a 1, this 1 comes into here. This becomes a 1. This is still a 0, a 0, a 0. Hey, X is now 1. That looks great, right? What happens next? We have 0, 0, 0, 1 going into our adder. We add 1 to that. The output of the adder is now 0, 0, 1, 0. Those get carried around these wires. This becomes a 0, 0, 1, 0. If the load line is still high after all this happens, and this happens in a few nanoseconds, if the load line is still high, this 0 on the D gets loaded into the latch, and now this becomes a 0. And this 1 gets loaded into the latch, and this becomes a 1. And now X is equal to 2. And if the load line is still high, this 2 will get added to a 1. The adder will put out a 3. We'll have a 1 coming in up here, and that 1 will get loaded in, and now X is equal to 3. And as long as this load line is high, X keeps incrementing. Now if we pull load down really fast, we may get it to shut down after it's only done this once, and X will be incremented by 1. But how quickly should we pull that load line down? Don't know. Certainly if we just raise load to 1 and leave it up for a minute, X is going to get incremented a whole bunch of times. So you see the problem here? The problem is, as long as load is high, we're continually doing X equals X plus 1. We're repeating this operation over and over and over again. And this operation doesn't always take the same amount of time. Remember, when you add numbers, if you do something like this, your circuitry is doing the same thing that you do. 0 plus 1 is 1. 0 plus 0 is 0, 0, 0. Right? The first thing it does is it changes this bit to a 1. But as soon as it does that, the sum is already correct, right? Because these 3 bits of x haven't changed. So as soon as your half adder figures out 0 plus 1 is 1, you've got the correct answer. But if you're doing this, the half adder is going to say 1 plus 1 is 0. Well, right now, x is equal to 0, 1, 1, 0. That's not correct. But you have a carry comes over here, 1 plus 1 is 0, with another carry. Well, now these 2 bits are correct, but this bit's still a 1. But that adder eventually adds that incoming carry of 1 to the 1, gets a 0. And so now you've got 4 zeros for x. That's not correct either. But finally, that last full adder will say I've got an incoming carry of 1 plus 0 is 1. Now your x is correct. But it takes roughly 4 times as long to get this answer as it did to get that answer. So in this case, that load line would need to stay high for 4 times as long as you needed in that first case. And this is a nightmare to try to deal with. Now there's people who deal with this. I like dealing with this myself. But it's kind of a nightmare because the timing is so touchy. Leave the load line high for too long and you end up adding multiple things. Leave the load line high for too little and you might not have enough time for the adder to give you a correct answer. And you end up with gibberish. So this is a fundamental problem with latches. And so here's how we can describe this. Latches are level-driven devices, meaning the level, high or low, of the load input determines what the latch does. Right? If the input's high, it's doing one thing. If the input's low, it's doing something else. But it only looks to see whether the latch is high or low. What we'd really like is what's called an edge-triggered device. Something that pays attention to the fact that right here, this input changed from a 0 to a 1. And we don't care what's happening over here, we don't care what's happening over here, we don't care what's happening here. We only want to pay attention to the fact that at this moment, this infinitesimal slice of time, this input changed from a 0 to a 1. There's an edge, okay, looks like an edge in the picture. So we want an edge triggered device. Instead of just loading the input in whenever the latch is high, we want to say load the input in at the moment that that input changes from 0 to 1. And if we do that, as soon as the load line changes right here, this 0, 0, 0, 1 will get loaded in here, and that's all that's ever going to happen. Doesn't matter how long the load line stays high, it's not going to load these inputs into the latch anymore. So this 1 is going to go to the adder, you're going to get a 2 coming up here. But that's not going to get loaded into these devices. It's only going to get loaded after the load line eventually goes down low again and then eventually goes high. And at that edge, that's when it'll take the 2 and load that into X. So if we can make an edge-triggered device instead of one that pays attention to the absolute level of the load line, we can use that to build these kinds of circuits. Okay, that's our basic prescription. So let's take a 5-minute break, and then we'll look at how to make an edge triggered device. And it's going to be really easy to do, given that we have level triggered devices.